Hi, I'm James Fort, a Senior Product Manager at Unity. I'll be joined by my teammate, Jonathan Hoggins, a Senior Engineer that works on our perception solutions. In this session, we'll be covering how to generate synthetic data for computer vision applications. Let's get started. So to set the frame here, we should describe that computer vision is showing up everywhere these days, across a number of different industry verticals. In the autonomous vehicle space, computer vision is used very heavily for detecting objects, detecting lane markings, signs, and traffic signals. In robotics, computer vision is used for robots to understand their environment and safely interact with humans and not clash with other objects that are in the environment, and also recognize the target products or components that they're trying to interact with. In retail, we're seeing applications like cashierless checkouts, inventory management systems, and other types of analysis. And in security, there is a need to identify potential threats, for example, in a home security camera type application. So producing a computer vision model these days is usually done through some sort of machine learning or deep learning process. And there is a huge data problem in doing this machine learning. Machine learning development itself is heavily data dependent. We're talking hundreds of thousands or sometimes millions or more images to be able to train a computer vision model. And collecting data for the machine learning process is often the most expensive loop in this whole process and the most time-consuming component of the process. It's often that the kind of data that you may need for your application cannot be collected for privacy reasons, and that could be just the kinds of terms that companies are setting with their customers for their privacy, or also even government regulations. And then the annotation of that data, which we'll talk about in a bit here, is both expensive and very error prone. Another point that maybe is a little bit less obvious is that if you're trying to create a computer vision application for some unforeseen events in the future, it's very difficult to use training data that you've collected from the real world to prepare for those unforeseen events. Because of course, you can only collect data of what has happened in the past. So these are some practical considerations to think through. Once you have the data, actually training with the real world data is really challenging. So we discussed how expensive it is to collect it, how time consuming it is. Another thing is that the data itself can be biased or insufficient in the sense that it may gear towards certain types of objects or certain classes of objects that are not necessarily the target objects that you may be trying to detect. And again, there are privacy and compliance issues that are real problems, especially with growing regulations in different government sectors. Okay, so let's talk about labeling a little bit, because this is a major part of the whole process of getting data from collection and getting it ready for the actual training process. So here we have an image. This may be from, let's say, an autonomous vehicle use case or some kind of smart city use case, where we've got a camera taking pictures of various vehicles and other things in the city environment, including buildings, pedestrians, stop signs, traffic lights. So to actually prepare this data for any kind of computer vision application, you need to have some kind of labels that basically tell the application what it's trying to detect or what it's trying to classify. And those labels are difficult to create and can be expensive and time consuming to create, also error prone. But another thing to consider is that depending on the specific task, the complexity of the labeling can increase rather dramatically. So at the simplest case, we have object detection. And in object detection, what we're doing in this case is we're just drawing a bounding box around the object. So think about yourself sitting in front of a tool for doing annotation and just dragging boxes as accurately as you can as a human annotator. As you know, companies are employing large groups of human annotators today to drag these boxes around the objects of interest. That's maybe a bit error prone, a bit complicated. Certainly another level of complexity is doing semantic segmentation, where not only are you dragging a box around an object, but you're also specifying each pixel that belongs to each object, basically painting by numbers for the different classes of objects. It's a much more difficult task to get right. There's yet another level of detail called instance segmentation, where not only are you giving a different color per class, but you're also giving a different color per instance within that class. So it's another layer of detail. And then you can have even more complex sort of layered types of segmentation like panoptic segmentation. And so you can see that the cost associated with each layer of information can increase quite a lot, and also the opportunity for error can increase quite a lot as you go up this hierarchy of complexity. If you look at the public data sets that are available today, many of which have these annotations available and have all sorts of objects in them, you may say, well, can't I just use these publicly available data sets because they're growing in availability? They are useful for a certain number of applications. And we see data sets like MNIST, the Kitty data set, the COCO data set, even the ImageNet data set, and they're becoming quite large and diverse. But the fact of the matter is that many computer vision applications in production are unique. And for unique computer vision applications, you're not likely to get the diversity in data that you need from a real world data set. So we have to consider other options. Now I would like to introduce synthetic data as a viable solution to the data problem for computer vision. Imagine a system that can produce your data set for you, including all of the annotations without you having to hand label a single image. With Unity, you can use our system to produce synthetic images at scale and include the labeling automatically. Synthetic data has been shown to be effective in a number of different situations. On the left, we see an autonomous vehicle situation, and in 2016, the Cynthia dataset was released, showing that models can be trained using real data and synthetic data better than models trained with real-world data alone. In 2017, OpenAI released some work in robotics, showing that using only synthetic data, you could train a detector with simple objects and simple configurations. And then some further research in 2019 showed that you could detect objects that are complex in simple configurations in retail environments. So what's the typical machine learning workflow, and how does this change between the real world data collection and model training paradigm and the synthetic data collection and model training paradigm? Let's look at the before and after, and we'll discuss some of the benefits. In the typical machine learning workflow, step one is to collect data from the real world. Again, this is often a time-consuming and potentially limited process in terms of the kind of data that you could collect. The next step is to go through the annotation process. And after annotating the data, you would transform the data into a format suitable for a machine learning pipeline. After you do the transformation task, you may identify, as you're getting ready to go to your training task, that you haven't necessarily annotated the data correctly. You may then need to go back and re-annotate the data. Again, you've probably hired some people to annotate the data for you. You may need to resync with that team, maybe a third party, to re-annotate this data. Again, costly and time consuming. So after you've transformed your correctly annotated data, you can then go to the next step of training your model. After you train your model, you then validate it against some real world test set. But after you do the validation, you may realize that you need further training. Or you may realize you need to go all the way back to the source and collect more data. Again, this could take a month or more and might involve coordinating with teams across the world. After you validate your model, you may then go on to deploy it, where all of a sudden, not only is the model seeing data like from your test set, but also unforeseen edge cases in the real production environment. This is the possible nightmare case where you realize you might have to, again, go collect more data to meet these edge cases. And this happens all the time for common machine learning tasks. Now let's switch to a view of the synthetic machine learning workflow and talk about how this is different. In the synthetic machine learning workflow, first you set up a synthetic environment in a tool like Unity. Then you generate your annotated data. And again, you get the annotation for free. A person doesn't have to manually annotate these frames. It comes out of the system that way. You then transform the data and go to your model training pipeline and train your model. And then you go through the validation step, after which you may need to do further training. But the nice thing here is after you validate, you may see that you need more data. All you have to do is go back to your system to generate more data instead of going back to the real world to collect more data and then annotate it again. This is orders of magnitude less expensive and faster. And then again, when you go to deploy the model, if you meet some edge cases that you weren't expecting, all you have to do is go back and generate more data that meets those edge cases. And maybe this means creating more assets that meet the edge case needs, or orienting the assets in different ways in the environment. So the key point here is that using synthetic data allows for rapid iteration and also a lot of hypothesis testing. What happens if I position the data in this way? How does this impact my model training process? Here in the AI organization at Unity, we have a team of computer vision researchers and tool developers that both create the perception package, which we'll discuss in this presentation a little bit more, and also do research to show how Unity can be used to solve computer vision problems. We chose to solve a problem in the retail space that takes advantage of a technique called domain randomization, which essentially takes objects and then randomizes many characteristics of the objects, including the layout of foreground images that are the images to be detected, the orientation of those images, lighting conditions, the layout of background objects, which are distractor objects, not the objects to be detected, but rather a chaotic background scene against which the foreground objects are placed. And so we went about doing this example, creating millions of synthetic images, all annotated with bounding boxes. You can see these rather chaotic looking images on the right with all sorts of post-processing effects and different orientations. The perception package was used for this work, and this is the open source package that we offer as part of our computer vision offering. With the perception package, you can randomly place objects in the context of a noisy background and generate bounding boxes, and then also generate all of the annotations required for training in terms of the actual metadata in JSON format. You can get a feel for the kinds of things that we randomize for this particular example, but keep in mind that the randomization framework that we provide as part of the perception package is highly customizable for any type of problem. Here we've randomized things like the density of images in the background, the density of occlusions, the lighting conditions, the hue of the objects, and things like white noise, blur, and other post-processing effects. Now, what did we do when we actually trained on this set? We ended up using about 400,000 synthetic images for our target classes, and we used an off-the-shelf faster RCNN model as our object detector. And that's a pretty common model in computer vision. We also created a real-world grocery data set for testing and benchmarking, where we collected 760 real-world training examples, with some of them being validation examples and some being real-world testing examples. So what did we get when we went about training this model? Well, here we see some results of a blend of synthetic and real-world data. And we see that with real-world images alone, we get a certain rate of precision and recall, which are key measures in the performance of a computer vision model. With synthetic data alone, we see lower performance across the board on these key measures. And then with synthetic plus real-world data, we see higher performance than the real-world data alone or the synthetic data alone. And we also see when we boost up the amount of synthetic data a little bit higher, we get even better results. So the key finding is that we can get quite good results with a combination of a small amount of real-world data and a large amount of synthetic data. Here are some examples of the performance of the model trained with the real-world data alone, and we can see many misdetections in red across different orientations, configurations, and lighting conditions. When we add the synthetic data into the mix, we see the number of misses goes down dramatically, and many of the objects in these images, at least, are detected correctly. Now I'd like to talk about a specific customer that we worked with to create a synthetic dataset for an aerospace application. The customer's goal is to build an iPad application to lock a digital twin onto an airplane in the real world and label defect points for repair. The customer's problem was that real-world data available didn't have the diversity required to train their locking model well. And the solution was that the Perception SDK and its randomization framework enabled the customer to produce a large and diverse data set for training this locking model. Domain randomization produced many variants in the rendered images, and you can see a couple on the right. We employed domain randomization to vary the sun and hangar lighting, angle, and intensity. We also varied the background material and rotation, the aircraft exterior selection, the aircraft exterior rotation in UV space, the aircraft exterior color shift to account for different types of lighting conditions, and tarmac versus epoxy flooring, 2 choices. Lastly, we varied the camera position around the plane to account for different orientations that the iPad application might have in respect to the plane. And then we produced ground truth formatting specific to the customer problem. Here we can see the ground truth format in a few images, including bounding boxes and metadata associated with the camera position, its rotation, the type of environment, the aircraft exterior, and the lighting intensity. These are all used for training purposes. We finally delivered a data set of 10,000 images and provided the completed project for the customer to use for continued image generation as they continued in their project. Now I'd like to talk a little bit about the Perception package. The Perception package is a Unity toolset for generation and ground truth annotation of synthetic datasets. It's flexible and it offers easy-to-use domain randomization capabilities. It offers a variety of labelers such as 2D and 3D bounding boxes, semantic and instance segmentation, and we'll have more labelers in the coming months. We have a step-by-step tutorial that takes you through easy use of the Perception package. We have 10 grocery objects that have already been scanned and are prepared for use with the Perception package. And we take you through the steps of generating an object detection dataset. We have foreground objects, which are the grocery objects to be detected, and then we have background objects, which are distractors for the model. Now I'd like to pass it off to John, who's going to take us through a demonstration of how to use the Perception package. John, take it away.
Thanks, James. Hi, everybody. I am John Hoggins, Senior Engineer on the Perception team. And let's just jump right into this little walkthrough. So I'm going to take you through a compressed version of the Perception tutorial that is available on the Perception GitHub repository. It's intended for people who are just getting started with Unity, and it uses some sample assets that are provided with the Perception package. So here I am creating a new project with Unity 2019.4. I'm going to call it Market Object Detector. And it's going to use the Universal Render Pipeline. Perception supports URP and HDRP at the moment. All right, so here's our URP default project with the sample scene. We're going to just delete that. And open the package manager here and add the com.unity.perception package using the get URL option. This is the best way to add it to your project at the moment because we are a preview package still, so it doesn't show up on that immediate list. Okay, so first thing we'll do in our scene is reset the camera transform and move it over to -10. So basically it's looking straight at the origin, directly at it, and then set this camera to orthographic. That's going to be sort of the way that we want it set up for this little scene generator. We'll remove the component that's on there and add the perception camera script to it. So the perception camera is what controls the rendering speed if you're tracking video, optimizes performance, and also generates the ground truth. So we're going to add the bounding box labeler and the rendered object info labeler, which adds some additional metrics for statistics. And then, first go in and grab the assets to do this tutorial. So it's going to come with some background objects, some foreground objects down there. And let's take a look at some of these foreground objects. So this is what we're going to try and detect. These sorts of guys here. And each of them has a script attached, labeling with the name of the script. And that's what we use to reference or to take that object and generate ground truth from it, wherever it is in the scene at runtime. Okay, so what we need to do then to get the ground truth generated is use these label config script, assets. So I'm going to just quickly fill out the names of the assets that we want to detect. This is what will end up getting fed into our machine learning training, and associate those configs with our ground truth generators. So you can have different configurations of your labels for different labelers if you want to. And with that, let's just see if how this works. So we're going to pull open the prefabs, grab one of those objects, put it in front of the camera, make it a bit bigger so it's easier to see. Okay, and then hit play. And then in a moment, we should see it there. Okay, and you can see the bounding box around the object, the label up there at the top, and you can see that it gets updated as I'm sort of manually rotating this thing. So if we hit stop and then go over to the console, it'll give us the path to the data set that was just generated there by the perception camera. And there it is on my system. Let's open that up and take a look at a data set. Okay, so here's the data set. Has the RGB folder that contains all of our RGB images. And we can see the bottle there rotating later on in the simulation. And then back up one, we have the dataset folder with JSON files that capture different aspects of the simulation as it was running. In this case, we have the captures file with a set of captures elements that contain information about the camera, time so far. There's our -10. The path to the RGB image, and then here's the bounding box, our lotion with the X, Y, width, and height. So we get all the bounding boxes there for our objects. So that's the basic format of this data set. It can be pretty easily consumed by Python. And we'll see a little bit more about that later. But for now, we can remove that object and actually make this generator a little bit more interesting. And the way to do that is to use a scenario. So we have the fixed length scenario, which is one scenario that comes with the perception package. And here you can configure the number of frames that we want to generate at once, and then frames per iteration. And you could set this to 10 or 100 if you wanted to create videos, for example, but we'll keep it at 1. And the magic happens in these randomizers. So here's a button now, add randomizer, and we're going to add the foreground object placement randomizer. This is the one that acts as our scene generator. We'll set the placement area to something that I figured out before would be a good spread to fill our whole camera. And then we go in and select the folder that contains all of our foreground objects so that they can be placed randomly in the frames. So we'll select the prefabs folder, and then here, okay, all of the prefabs that were in that folder are then populated in this list. Let's see how that works. Okay, there we go. So yeah, we've got a bunch of objects randomly selected from our list. They're all getting bounding boxes. That's great. It generates a little data set here. We're noticing that all the objects are facing away from us, and all the same orientation. So let's add another randomizer called the rotation randomizer. And this is a tag-based randomizer. So in order to apply the random rotations, we have to change the objects that we want to randomize and add the rotation randomizer tag to it. So that randomizer will pick up on all objects that have this tag each iteration and randomize its orientation. Okay, so let's see that going now. Great. Okay, much better. Now we have objects in random orientations everywhere, and that gives us a good coverage of the different angles that you might see this in the real world. Okay, so one more thing before we call this good for now, which is the background objects. We'll set a depth of 5, so that gets it a bit behind the foreground objects. Set the separation distance to make a large number of them, fill up the whole region, and then select the background prefabs that come with this tutorial. Okay, here we go. And then the thing to notice about these specific objects is that they're just a handful of primitives, spheres and cylinders and so on, with no interesting texture. So to make it more interesting, we'll add a texture randomizer here, in which we get to select a set of textures to apply to the objects that we mark. So in this case, go to background textures, select that folder, and then we get a whole bunch of images of in this case, fruit, that we're going to map onto these objects. We'll select all of those background objects, add the texture randomizer tag, and also the rotation randomizer tag for good measure. And now they should be getting a random texture each frame. And then also, we'll move the rotation randomizer down in the list to make sure that it runs after the background object generation. Okay, so here's something now it's much more interesting. We have background distractors that will help make sure that our model identifies not only what is our objects of interest, but also what is not. So I'm going to let this data set get generated with about 100 frames, and we'll pull it open in a Jupyter notebook and see how this can be consumed from Python. All right, so we'll pull up Docker, and we're going to bind the path to this data set as a volume. We'll bind the path just above it. You'll see why. And we're going to use dataset insights, which is the Python package that we created for helping you to consume these perception data sets from Python and do model training and statistics. Okay, so here's our Jupyter notebook opening up the perception statistics notebook, which comes with dataset insights. I'm going to paste in the path here and just reference data / the folder name with our dataset and run this notebook. So this notebook contains examples of how to use dataset insights to consume the data and shows off what's in it. So there's bounding boxes, rendered object info. We have statistics on number of images here and number of objects present in the whole data set. About 200, that's a good distribution. Objects per image and so on. And these statistics are super valuable for understanding what's going on in the data set, because I'm not going to look through 100 frames, much less 100,000 frames, to make sure that everything is working. So these aggregated numbers really help us understand what's going on there and find issues if any come up. So visible pixels per object, super useful to see if we have very large or small objects. And then down below, we can look at the captures themselves and visualize the data. So you can go through and look at each image here. This is great if you're doing it locally, but then also if you're generating very large data sets on Unity simulation, you can use this to visualize some of the images. Okay, so there's one more thing that we want to do, though, to make this really useful. So I'm going to pull in some scripts that I wrote before. They're actually very simple, but were some custom scripts. This is a custom randomizer, light color randomizer. We're going to change the light color and set the value to between 0.5 and 1. Value is sort of the light intensity. And then put the color randomizer tag onto the light and hit go. Oh, but first of all, we're going to remove the skybox and switch the ambient color to something a little bit subdued so that we get some full effect of the light. Okay, this is much better. So which should help the model generalize better in different lighting conditions with these different colored lights. And this is just really showing the iteration flow that we expect everyone using the perception workflow to be going through. Okay, so let's take that data set that we just generated with the light randomization, run statistics again. We could have added new statistics maybe for that light if we wanted to. I'll leave that up to you. But then once this is done, we'll be able to see the images again and just verify, okay, that this is looking like we expect, and it looks pretty good. So that's the idea of how to use Unity for synthetic data using the perception package. And where you would go from here is either generating larger data sets on either locally or on Unity simulation, where you could get hundreds of thousands of images in a few minutes. And then also, of course, training a model. So we have examples in Dataset Insights of how to train vision models using these data sets, and it should be straightforward to integrate. So that gives you a quick overview there. And with that, I will turn it back to James.
We've covered a lot of material today, so I'd like to summarize. Training modern deep learning models requires increasingly large datasets, which are expensive and time-consuming to collect. Using synthetic data circumvents some of the biggest challenges of data collection and annotation. You can create highly randomized synthetic datasets with Unity's Perception package, and you can get started today with the Perception tutorial. And now let's take a brief look into what's coming in 2021. You can expect that we'll have an AI-ready content database and some environment generators for specific computer vision problems. I'm going to restart that slide. And now let's take a brief look into what's coming in 2021. You can expect that we'll have an AI-ready content database and some environment generators for specific computer vision problems. We'll have labelers for additional computer vision tasks, and we'll have integration of different types of sensor models beyond just RGB camera sensors. And lastly, you can expect we'll have a new and simplified interface for data generation. We invite you to connect with our product team using the following email address: perception@unity3d.com. Thank you for your time today.
All right, cool. That's the end of the video, obviously. So let's get our presenters and panelists up to answer any questions. Hi, John. Hi, James.
Hey, Sam.
Hey there. It's good to be here.
Great to have you on, and great presentation. So what questions do we have for the team from Unity? I saw there was some activity in the chat, but it looks like those questions have been answered so far. Interesting comment, though, from Thomas, who mentioned that this is a challenge that he's seen before in the past, and his team had to do all of this stuff by hand. I imagine you see a lot of teams that have wrangled with all this by hand previously.
Yeah, when I joined this group, it was sort of the first thing that was said was, we know people out there are doing all of this work by hand, working with rendering, working with randomization, and we should just solve this once for everyone, right? So that was really what we set out to do with this, and see if we can really, push this whole field forward a bit in the process.
Very cool.
And I
John,
guess I
let's
would say, in addition to that, we've gone through several iterations of what our randomization framework looks like. So we came up with some very specific randomizers for first couple of projects, and since then we've sort of generalized our randomization framework and made it very sort of extensible and open-ended.
Awesome.
So we have a question here from another one from Thomas, talking about how does perception integrate with ML agents? It's a really interesting question, actually one that we also want to explore a bit more, but really perception and ML agents right now are serving sort of two tasks, right? One is perception is building these sort of offline data sets for training vision models, whereas ML agents is really focused on the reinforcement learning and training behaviors. They also have some sort of visual aspects, but I think this is something in the next 6 months we're going to go deeper on. Any of you, anybody else have anything to add to that?
I guess, yeah, what I'll add to that is maybe just a refresher for some folks that may not know ML agents. ML agents is basically an open source project that Unity's offered for quite some time to do reinforcement learning training and connect it with Unity as an environment for that training. And there's a lot of interest in using that in the context of gaming. There's also a lot of interest in using that in the context of like robotics tasks. So as you think about robotics as a use case, you can think about a vision component and then a sort of behavior learning component from a reinforcement learning perspective. And as we move towards having better and better computer vision capabilities, you can think about training the computer vision sort of like module of a robot and then integrating that trained module into a reinforcement learning sort of training loop with ML agents. And so I think you'll see these two things sort of merging into an overarching solution for robotics like use cases and autonomous use cases as we go forward.
Awesome. There's a question in the Q&A panel. What are the checks and balances for realistic images plus backgrounds? Or is the idea that ML models need a vast amount of quote unquote nonsense data for generalizability and not locking onto extraneous stuff not related to the objects of interest?
Yeah, I can take this one. I think the general idea for the reason that we create these background extractor is we want to make sure that the image that was created wasn't too obvious for the model to learn the program, because we know this ML model is very sensitive to the way the texture was created. So it's very easy to overfit to know, to be able to tell the difference between the foreground and background. So that's one of the reasons that we kind of want to make these kind of only looking background, so that it's more like if the foreground is randomized, so that the background also needs to be randomized, and then we want to keep them as more close aligned as possible. But we do think that this is also a direction that we need to explore more, because I mean, so far we're talking about based on the hunch of how we generate the data, but we didn't actually do enough comparison or enough detail in terms of different way to generate a background to see how the model performance respond to different way to generalize the background.
There's
Sean?
another one. Oh, go ahead, James.
Yeah, I was just going to ask you, Sean, how much familiarity, I'm thinking of the work that Salehe and our team has been doing around human pose estimation. There's a question here about using synthetic data for detecting real world people that are animated and how we can randomize around that. And I somewhat generically described that we are doing work around having 3D human models with randomization across different traits of humans, and then with randomization in their animations as well for different poses. for pose estimation. So this is an active area of work for us. Yutron, I don't know if you have familiarity more with Salehi's work, or if we should maybe take that one offline a little bit.
I think we can probably take it offline, but I can quickly comment on that. I think the way we think about these experiments, we want to kind of do that in stages, right? Because the first thing that we know on high level want to do is the post randomization, the different human. But then we can think about the next level is you might want to actually randomize the human face or other things. But then, right, it all depends on how much detail we want to add to that, and then we will gradually make the project a little bit more complex for different case and different experiment that people are interested.
Yeah, I think one thing I want to say as well is that you know, in any kind of data set creation, you know, any kind of synthetic data set creation, we're using 3D assets as the basis for what we're doing. And so, you know, there's the common question of, well, where do these assets come from? And if you have something that's based on, let's say, like an environment, maybe there are ways to create scans of environments, and those can be quite diverse per application. Something that we've thought of as a team is one way that we can serve our customers best is by thinking about the objects or the environments or the scenes or the assets that are most common across as many applications as possible. And there are quite a number of applications for human pose estimation, or that involve sort of human pose estimation. And so we've begun investing in making sure that we have the right kinds of models of humans at the right level of fidelity for different types of applications. And we have a prioritization order there, thinking mostly about human pose estimation from somewhat of a distance as a start. So like different joint articulation angles, and getting some models in place for that. So if there are folks that have interest in doing this kind of human pose estimation work with synthetic data, we can definitely talk about that. And you know, we have a starting point there.
There's an interesting question about the use of synthetic data in areas like healthcare. James, I've even talked to lots of people trying to use perception in different areas.
I'm trying to find that
This
one.
is
Is that in the Q&A?
From Ari in the chat.
In the chat. Why don't I see?
38, great presentation. How much is the
I see.
impact of using perception?
Healthcare. It's interesting. So I do recall speaking to at least a couple of researchers last year that were interested in using synthetic data for basically doing AI-assisted surgery applications. And the interest there was to be able to detect you know, malignant cells and tumors and polyps and things like that, where you know, otherwise, just to reduce the risk of having to do, like, to increase the efficacy of biopsies and things like that. So I think that there is, you know, quite some value and interest in generating data sets like that. Again, it comes down to how do you create the content and what kinds of data sets are necessary. Like, do you have to create geometrically accurate data sets of a liver to be able to detect a polyp or something like that? Or do you need, or can it be more abstract in nature such that you're just representing the features with the underlying content and data? So I think there are some, you know, pretty large challenges around content for certain aspects of doing things in healthcare. That's one use case that came to mind based on discussions that I've had, but you know, I think you can think of maybe generating synthetic data to help with X-ray detection, things like this. One of the nice things about synthetic data is that it's, I would say, probably somewhat easier to create volumetric versions of the data than it would be to collect volumetric data in certain cases. So I think there are use cases for things like CT scan. Yeah, it's a broad area that I think you know, we've only scratched the surface on in terms of what we've heard from our customers and interest.
Yeah, there's an interesting question here from Jaime Espinoza. Do you have tools or methods for capturing the models rather than building from scratch on your platform? And the end results will be closely linked to the quality of the model generating the synthetic data. So when you're saying models here, I'm going to assume you're talking about the 3D models that we use to actually do the rendering and the randomization. So yeah, correct this. Yeah, so that's right. Yeah, there are a number of avenues to getting content into Unity. You can use existing sort of 3D representations of objects, so CAD models. There are vast libraries of 3D sort of art online that you can use, which we've actually leveraged pretty successfully in a couple of projects. There's the Unity Asset Store, which is one of those sort of marketplaces for 3D content. But then in addition to that, we're able to import 3D scans from various sort of 3D scanning tools. There are a number of them on iPhone and Android. There are off-the-shelf tools that are a bit more high quality that are built for manufacturing purposes that will actually use things like structured light or LiDAR in order to do very accurate 3D scans. And those will come directly into Unity. The interesting kind of thing about the quality of the synthetic data, this is an open sort of area of research. Definitely interested to see what everyone discovers here. But even if you get one scan of an object, it might not be enough. You may want to get multiple scans because the scanning technique itself might introduce some noise in the 3D model, or you might want, if it's a non-rigid body, you might want multiple sort of positions for that, because really it's almost like that 3D model becomes the source of all the examples of that object you get in your data set, right? So again, more variety. But you can get 5 models instead of 5,000 images. So that's still the power of it. And then there's a side portion here on behavioral modeling. So for human, like pose detection, something we're working on right now, there is a vast library of animations out there for humans, essentially putting them in different positions, sitting, standing, drinking, walking, talking, all those things, jumping up and down. You could design all of those animations by an animator and then apply them to maybe hundreds of different human models to get a nice multiplicative effect. 100 models times 1,000 animations times 5 seconds each is a lot of examples.
I see an interesting question from Ari. Insightful that the mix of real and synthetic data is giving higher precision. Curious, is there a way to validate the synthetic data generated before learning on the synthetic data that's generated? One thing that John did show in the scope of the demonstration was this dataset insights sort of notebook that we have been using, which provides some statistical information about the dataset, things like counts of objects, et cetera. So that can provide, A/B comparisons in data sets and just some idea of what the contents of that data set is before you run it through the model training pipeline. But another thing that we really want to do is make sure that this data generator is as closely tied to the model training pipeline as possible. And the idea there is, you shouldn't have to have necessarily completely separable phases of data set generation and model training, but rather you can start to think of it as one continuous pipeline. And maybe in the beginning, you're not using the full architecture of the final model, but you could have a small test architecture, a small test network that you could hook up to the dataset generator that's representative enough to give directional indication of the quality of the data set, and just start rapidly generating data sets with different parameterized values, and then see directionally, are you moving in the right direction? And we've actually seen customers do this in certain projects to sort of hone in on you know, let's say the optimized data set for the application. And then once you have the right directional indicator, that's when you can go at scale and start generating, let's say, 1 million+ images, once you start to have confidence with this preliminary validation method.
You know, there's one sort of addition here from Jaime talking about what kind of behaviors you might want to model, like the flex of the wings in a plane. I think it's kind of worth bringing up the, you know, the long history and the vast size of tools for building video games, right? You can kind of imagine the different complexities of rendering, of animation, of deformation that are present in, you know, some of the highest quality games these days. And the tools for building that are really what we're trying to bring to machine learning. So, you know, flexing in the wings of a plane is actually a fairly straightforward thing to implement from an artist perspective, building out that plane and associating the different parts of that with a skeleton. We call them a skeleton with bones, where you could maybe move the tip of the wing, and the rest of the wing would sort of deform properly along with that movement. So really, you know, that's the power of the system, is that if you can imagine it, it's possible. It's just a matter of, you know, some things are more straightforward than others, and you might have to go deeper into the engine to get to some of those other features. And so that's also sort of part of what we're trying to explore right now, is how can we give you this vast toolbox to build whatever kind of dataset generator you want, but then also provide, you know, a handful of really the most valuable features to put together dataset generators without vast experience in, you know, video games and 3D art and these sorts of tools. So we're really exploring, you know, how do we make this easier for ML engineers to build datasets. It is like using GTA to train self-driving cars. Yeah, exactly. Except now you have full control over that thing.
There's a question from Ari about, is there any way to validate a synthetic data generated before learning on them? I mean, this is actually a question we keep banging on our head. What is the best way for us to validate the data? Right now, the only thing that we have is looking at statistics, and then kind of you have to use your best judgment to guess, or what could actually went well and what could go wrong. But I could imagine that there might be different research direction, like maybe you look at the distribution of data in some novel way that will help you to get insight into that. But like, to be honest, I think right now we'll just be limited on statistics right now. But I was hoping that in the community that we can come up with a better way to validate the data before you feed into any model training, because everybody knows model training is very costly and it takes time to actually wait until get to results. So it would be good that we can develop some method that can do the validation upfront, and then you can fix the error before that you actually went ahead train a real model.
Yeah, again, and I'll just emphasize, you could probably train on smaller architectures at less cost to get some directional indicator as a starting point. Okay, I think we covered all the questions that I saw in the chat.
There's one more just came in from Ari. Is there some visibility in the cost factor as well while doing data generation?
Yeah, absolutely. So we've done, I mean, so essentially, you're translating the cost of data collection and data annotation into the cost of computing the data set and the amount of time it takes to set up the data set generator. And we do have, we could probably share some numbers at another time, but we do have enough cases where customers have, said that something like multiple hundreds of thousands of dollars and multiple months essentially can get translated down into much a fraction of that cost and something like a number of weeks to generate a data set for different applications. The reason I'm being a little bit non-descriptive in actual numbers is because I'm waiting on a case study to come out here that I'll be able to present to folks in something like a month with a particular customer that we worked with, but substantial savings in terms of both time and cost.
Yeah, and something to just kind of quickly add to that, when you're talking about at least, the dollar cost of generating data sets, you do have a couple of options, right? Like using the Unity editor and sort of going through the flow that we showed earlier, you can generate fairly large data sets just on your local machine, sort of depending on what hardware you have. And then it's just the cost of your electricity there. But then when it comes to generating like very large data sets, hundreds of thousands of images, it's generally worthwhile to move into the cloud to generate these at scale. And then you can leverage some of the services that we've begun to offer around at scale data set generation, which I don't know, James can speak more to the cost on that, but I think it's not very expensive.
Yeah, we're still working on finalizing pricing there. That's why I'm not quite getting into it here, but we can definitely talk in individual conversations, and we will have pricing that's published once it's available.
Awesome. Thanks so much, John, James, and Yu-Chen. Great presentation, and appreciate all of the attention to the questions that came in. For those who may have additional questions, I would suggest reaching out to the team via their booth on the platform or the messaging. Lots of ways to engage with them. Thanks so much for your presentation.
Thanks so much, Sam. Really appreciate it.
Thanks. Good to be here.